Hi y'all, we are now going to turn from microscale diffusion to macroscale actions that can help us to accelerate mixing. So as we've seen, molecular diffusion is very slow, especially if you leave it to act on its own, as you see in the animation on the left. However, we can significantly accelerate this process by adding an additional macroscale action. For instance, there is stirring being imposed on the right from some sort of an external source. And this addition of stirring on top of diffusion is taking something that would take weeks or months and causing it to take a matter of seconds. So the example I just showed was an external action, but there are also internal mechanisms within a fluid that can help to accelerate diffusion. And this is what's known as turbulence. So when a flow becomes unstable, there are going to be these instantaneous motions within the fluid where it's moving in all sorts of directions that vary in both space and time. And you can see an example of this just downstream of the spillway, where you get this water moving in all sorts of directions, and that direction is varying across the time of the animation, but also across the volume of the flow. There are a large number of processes for this turbulence to be generated within lakes and reservoirs. However, we're going to leave that for a future discussion in a separate lecture, and for now we're just going to focus on general characteristics of the turbulence that apply to any fluid and not just a lake and reservoir. So in terms of these turbulent motions that I mentioned, they can directly carry different quantities that are varying across different regions of the fluid. So for instance, in this animation here at the bottom, we have water that is a pink color dye at the top and a yellow color dye at the bottom, and they are initially separated by a plate that is then removed, and then later parts of the channel allow there to be mixing of these two dyed regions across the dashed line representing a mixing plane. And so these turbulent motions that go in various directions include ones that move vertically across the plane, so you get yellow regions of fluid moving up into the pink region, and vice versa, pink regions moving down into the yellow region. This motion that carries the different quantities, so the different colors in this animation, represents something known as advection, which is transporting portions of the fluid by a bulk or macroscale motion. And in this animation, technically speaking, you are looking at how the flow is varying across the length of the channel. However, you can also think of it as a time process if you are following the fate of an individual flow parcel as it moves down, and it may come down below and then eventually come back up, etc. And as I mentioned, you can get this motion that is directly by bulk movement coming across our mixing plane. This movement that is coming directly across the plane can be defined using this idea of fluctuations based on the velocity signal that you would get at the plane. So if you look at the flow that is moving past a particular point that is fixed along the plane, and you look at the vertical velocity component, so how fast the flow is moving up and down, you're going to get this variability in time that's representing these individual fluctuations. These fluctuations are directly moving a portion of the fluid that used to be below the plane to directly above the plane, and vice versa, and it is carrying with it the quantities that are either higher and lower and carrying it into the opposite region. So even though there is no mean vertical velocity here, if you take the average across this signal, it's equal to 0, you still get these short snippets of time in which there is fluid being carried up above the mixing plane and fluid being carried down, and you can simply identify that by the sign of the vertical velocity. You can see from this example signal that these fluctuations are very complicated, and that it would be very difficult or even impossible to try and predict from one moment to the next what this vertical velocity is going to be doing. So instead of trying to deterministically say what is happening at a given moment, we need to find a way to collectively describe the net effect of all the fluctuations and how it impacts the overall mixing process. In order to do this, what we need to do now is turn to the governing conservation equations for the motion of a fluid, and that's what we're going to discuss in the next video.